right? Now, another force that you would encounter, so we spoke of contact forces, friction and normal. The other forces that we encounter is forces in strings. Strings. What's a string? It's an inextensible entity. If this is a string AB, then what characterizes a string? A string is characterized by the fact that it is inextensible. Its length cannot be changed. Inextensible entity, that's a string. To begin with, I will talk of a light string. When I talk of a light string, what does it mean? It means mass of the string is practically zero. Mass of the string is practically zero. That's a light string, or very low mass. That's a light string. Now, if the two ends of the string are pulled with a force F each, if two ends of a string are pulled with a force F each, then every segment of the string feels a certain force. A stretching force is felt by every section of the string. So if this is a cross section of the string, it will experience a stretching force at this cross section. It will experience a stretching force at this cross section, right? The stretching force at a given cross section, this is a cross section of the string. The stretching force at a given cross section this is a cross section, say PP, cross section PP, is called the tension force, This is a cross section of the string. There is a segment of the string to the right of this cross section, and there is a segment of the string to the left of this cross section. Now, when I say the tension at this cross section is T, that means the stretching at this cross section is T newtons. What does it mean? It means, when I say the tension at this cross section is T, it means the segment, there is a segment AP. There is a segment AP of this string, right? At P, if I say the tension is T, that means the force at P is T. What it means is, this T would pull AP with a force T. This T will pull AP. This tension will pull AP with a force T. It will pull. This T will pull AP. Also, if I look at the segment PB, then at P again the force is T, but as far as PB is concerned, the tension will pull PB, will exert a force on PB leftwards. The tension at P will pull AP, the tension at P will pull PB. That means at P, tension exists both to the right as well as to the left. What does the rightward tension do? The rightward tension at P pulls AP. That means exerts on AP a rightward force. There is a leftward tension at P. What does this leftward tension at P do? It pulls BP leftward. That means tension at P is both to the right as well as to the left. That is what causes the stretching effect on the string. But the direction of T at a given point P will depend on whether I am looking at PB or I am looking at PA. Suppose I am looking at PA, then PA will tell you, suppose you ask PA, suppose PA had life, it had brains, it could feel, it could sense, then PA will tell you that tension is pulling me to the right with a force T. And if you ask PB what tension at P is doing, then PB will tell you it is pulling me leftward with a force T. So at P, there is a stretching force both to the right as well as to the left. This T acts on AP, whereas this T acts on PB. Right? This is the character of the stretching force. This force is called tension force. At a given point, it will exist in both directions. At a given point, it will exist in both directions. One direction will act on one segment, the other direction will act on the other segment. Right? So if you look at the free body diagram of AP, then at P, tension will act to the right. And there is a force F to the left. There is a force F to the left. Yes or no? And if you look at PB, there is T acting leftwards like this. And there is this F acting rightwards. Yes or no? Yes or no? Now, if you look at AB, then there is a force F to the right, as you can see, and there is a force F to the left. And there is tension at every P of the string. But if you look at AB, then the tension at any given P would be an internal force. It will cancel off in pairs. But if you look at AP, then this T will be rightwards. If you look at PB, this T will be leftwards. So for AP, this is not balanced. For PB, this is not balanced. But for AB, this T balances off. It cancels off in pairs. Yes or no? Now, what does tension do to any given element? It pulls that element. Normal forces will push, but tension forces will pull. Tension will never push. It will always pull. Tension will always pull. Such is the character of tension forces. Now, the important thing is, so tension will always pull. It will never push. And at a given point, it's a stretching force in both directions. It's a stretching force in both directions. One acts on one segment, the other one acts on the other segment. This is the trait of forces of tension. This is the trait of forces of tension. Now, suppose, so in a situation like this, the one that I demonstrated, suppose this string is light. AB is a light string. There is F acting to the right and there is F acting to the left. Right? And there is any point P in the string. Suppose, so the string is light, that means mass of the string is practically 0. And I want to compute the tension at P. Now AB, if I look at the free body diagram of AB, AB will not tell me what's the tension at P. It's an internal story for AB. But if you create a divide at P and then ask PB or ask PA, they will then tell you what the tension at P is. That means now I look at the free body diagram of BP, for example. So in AB, tension was acting to the right, it was acting to the left at P. But if you look at PB alone, there is force F acting to the left, there is T acting to the right. There is T acting to the right. Now, realize, if you looked at AB, the net force acting on AB is 0. F minus F, yes or no? That means, what's the acceleration of AB? What's the acceleration of AB? 0. So, if the acceleration of AB is 0, acceleration of every element of AB will be 0. So, acceleration of PB will also be 0. Yes or no? So, acceleration of PB is also 0. If acceleration of PB is 0, that means the net force on PB must be 0. That means T must be equal to F. That means at every point of the string, the tension will be equal to the two forces F applied at the two extremities of the string. And the tension will be the same at every point, and it will be equal to F. That means if I have a light string and there is 10 newtons like this, and there is 10 newtons like this, then at every point of the string, the tension will be 0. In fact, in this case, even if the string was not light, even if the string had mass, but was in equilibrium, if the string was having mass and was in equilibrium, say if the string was of, this is AB, if the string was of length, say 10 meters, and had a mass, uniform string, and had a mass 10 kg. That means its mass per unit length would be what? 1 kg per meter is the mass per unit length. 1 kg per meter is the mass per unit length. And I'm pulling it with a force 10 newtons like this. And I'm pulling it with a force 10 newtons like this. Alright. Now if I look at the free body diagram of AB, what's the acceleration of AB? 0. So acceleration of every element of AB will also be 0. Right? Acceleration of AB is 0. Yes or no? So every element of the string will have 0 acceleration. Now if I want to find the tension at a point P of the string, at a distance x from A, at a distance x from A, I want to find the tension. Look at the free body diagram of AP. If I look at the free body diagram of AP, what are the forces acting at A? There is 10 newtons to the left. At P, there is tension in both directions. T like this as well as like this. But if you ask AP, what does it perceive as the tension? T to the right. And AP is in equilibrium. AP is in equilibrium because acceleration of every element of the string is 0. So T must be equal to 10 newtons in this case. And do you realize it does not depend on where P is located? It does not depend on where P is located. That means if a string is in equilibrium as shown horizontally, then at every point of the string, the tension would be the same and equal to, say, the two forces F and F. But doesn't mean that tension will always be the same at every point of a string. I could have had a situation like this. Can I wipe this off? Suppose I have a string of this kind. This is a string fixed to the ceiling, and there is mass equal to 10 kgs hanging vertically in the string. And this string, say, is of length 2 meters and has a mass, say, 16 kgs, has a mass 16 kgs. Okay? And it's uniform. That means its mass per unit length, lambda. What is its mass per unit length? Is 8 kilograms per meter. 8 kilograms per meter is the mass per unit length of the string. Now, I want to find the tension at A, the tension at B. This is the section B. Say this is 3/4 of a meter here, and tension at C, which is, say, let me call this 1/4 of a meter, and let me call this 3/4 of a meter, is C. All right. I want to find the tensions at A, B, and C. Now, what I do is, I look at a free body like this. Free body comprising the mass 10 kgs. I look at this free body diagram, the rope plus the mass as one unit. Now do you realize that the string at A would want to pull the ceiling downwards? So the ceiling will exert at A a force upwards, which would be the tension at A. Which would be the tension at A. The rope at A will want to pull the ceiling downwards with a certain force. The ceiling would want to pull the rope upwards with a certain force, right? So at A, if the tension is TA, then the ceiling will exert on the rope an upward force, right? Now, what are the other forces acting on the system? The weight of this and the weight of this downwards. What's the weight of this? 160 newtons. What's the weight of this? 100 newtons. So the total weight would be 260 newtons. 16 plus 10, 26 kg weight. Means 260 newtons downwards. That's the weight acting downwards of the system. And the whole thing is in equilibrium. TA must be equal to 260 newtons. TA must be 260 newtons. Yes or no? Now, let me find out the tension at B. So to find out the tension at B, I will have to create a divided B and then either look at the free body diagram of AB or look at the free body diagram of the body below B. I could do that, right? Suppose I look at AB, free body diagram of AB, right? If I look at the free body diagram of AB, at A, there is a TA which is 260 newtons acting upwards, which we have computed, which is the force that the ceiling exerts on the rope, TA equal to 260 newtons. Now this length is 1/4 of a meter, right? What's the mass of AB? Mass per unit length is 8 kilograms per meter into mass per unit length, into the length. 8 kilograms per meter into 1/4. That means 2 kgs, right? Per meter 8 kilograms, so 1/4 meter 2 kgs. So mass of AB is 2 kgs, right? And at B, there is a tension upwards as well as downwards, right? In both directions there will be tension, right? This TB acts on AB, whereas this TB acts on this unit. So if I am looking at AB, then what's my relevant TB? This TB. So at B, there is a pulling force TB like this. And this whole thing is in equilibrium. Because this whole thing was equilibrium, every element is in equilibrium. That means now there is also weight of this 2 kg acting downwards, which is 20 newtons downwards. And the system is in equilibrium under the influence of these forces. That means TA must be 20 newtons, the weight acting downwards, plus TB. So TB then turns out to be TA minus 20 newtons, which is 240 newtons, right? I could have also obtained the tension at B by looking at the free body diagram of this whole thing. How? At B, this time, if I look at this portion, then tension at this would be upwards, TB, right? This time it's going to be upwards. Now this was 2 kgs. So this must be 14 kgs, isn't it? Because the total mass of the rope is 16 kgs. This we have computed as 2 kgs. So this part must be 14 kgs. So this is 14 kgs of this rope plus there is 10 kg of this, right? So that means there is 24 kgs in all. That means there is 240 newtons acting downwards. There is 240 newtons acting downwards. right? 14 plus 10, 24 into 10, right? This is the sum total of all forces. Hey, do you realize it's an equilibrium under the influence of these forces? TB must be therefore 240 newtons. Same as what we got earlier. TB turns out to be 240 newtons. Similarly, you can find the tension at C also. Suppose at this, at D, which is this point, I want to find the tension. So I isolate this mass, 10 kg mass. At D, that rope would want to pull the mass upwards with a force equal to TD. And the weight is 100 newtons downwards, 10 kgs. So TD must be 100 newtons. Under equilibrium conditions. Yes or no? This is the character of forces in strings. This is the character of forces in strings. Always pulling in nature. And if it's a light inextensible string, mostly you will find the same tension at every point of the string. If it's a string with a weight, then there can be a situation where every point could be under the same tension, but there can be a situation where every point could be under different values of tension. That's possible, right? But in general, most cases, I can tell you, tension in a light inextensible string would be the same at every point of the string. In general, say for example, I'll just show you, but there is nothing cardinal about this. Suppose there is this string, and it is being pulled to the right with a force F1 and to the left with a force F2. Or say only to the right with a force F1. And I want to find the tension T at a distance x from this end. I want to find the tension T at a distance x from this end. What I do is, I look at the free body diagram of this portion, x units. What are the forces acting on it? F1 to the right. And there will be T acting to the left. Suppose A is the acceleration of this. Then do you realize that F minus T must be mass of this segment S into acceleration? But this is negligible because it's a light string. I'm talking of a light string. That will give me T equal to F. It will give me T equal to F because this is practically equal to 0. String being light, ms is practically 0. So T will be equal to F. That means, and this T does not depend on x. That means this T will be the same at every point of this string. So mostly in a light inextensible string, I will not generalize this, but in most cases you will find the tension being the same at every point of a string. The direction would be given by the element you are evaluating. It will always be pulling in character. Such is the effect of tension, right? Got me?